Here I'm gonna cover the concept map for waves, Unit 3. So waves, let's first look at here. So waves are, we could distinguish waves from transverse waves and longitudinal waves. And the definition of transverse wave is that the disturbance is perpendicular to the direction of the wave. But for longitudinal waves, the disturbance would be parallel to the direction of the waves. And this is the wave speed equation. And if we take a look at the snapshot graph and the history graph here, the snapshot graph is saying that we're looking at the displacement of each particle at t is equals to 0 seconds. It's like t is equals to a certain time. So in this this diagram here, at t is equals to 0, then the displacement of all the transverse waves would look like this. But for history graph, we're looking at one particle instead of the whole wave. So for one particle, it's gonna move down and then move up as time is going forwards. So for transverse waves, we're saying that the snapshot graph is like the picture of the wave. But for history graph, we're saying that it's like the story of a particle. And if we're looking at longitudinal waves instead, the snapshot graph, when we're saying that we take a particular time and we stop the whole wave, then the same thing we can have some graph similar to the transverse wave, but in this case the snapshot graph would be the representation of the wave, because this is not really what the wave looks like, because it is longitudinal wave, but it represents the wave if we convert it back to what the longitudinal wave is about. And the same thing with the history graph, is just the story of the particle. So as we move further, we could look at how different types of waves is involved. The first waves is the electromagnetic waves, which we do not talk much here because this is not the focus of the unit, but this is the equation that we'll be using if we're talking about electromagnetic waves, which we talk about in waves optics. And there's the matter waves, which we talk about in the next unit about quantum mechanics. And the key waves we're focusing is the mechanical waves, which means that it requires a medium. And for mechanical waves, we could look at the traveling waves or the sinusoidal waves, or what is called the harmonic waves. And there's a mathematical model for it, and I included the phase diagram for it. But basically, it's classified into 1D, 2D, and 3D. For 1D, we could visualize this as a string. And when we're looking at the string, then we could actually see that the velocity of the string would relate to the tension of it and the linear mass density. And for 2D waves, we're usually looking at ripples, but it's not really a focus here. But when we're looking at waves, we will look at the superposition here, as we talk about later. But ripple is another 2D waves. And for 3D waves, we'll focus on sound. And this equation is very useful. This is not really an equation. This is like the constant. That is very useful when we have to deal with the frequency or lambda, because the velocity of sound would be given for us to determine the wavelength of the wave given its frequency. So when there's two traveling waves, then there would be a superposition, or what we call the interference. There could be constructive interference and destructive interference, and it is governed by this equation. So notice that to determine if it is constructive interference or destructive interference, we have to take in two factors. The first is the path difference, and the second is the phase difference, the phase constant difference. And if m is integer and it satisfies m2 pi, then it would be constructive, and it would be destructive if it satisfies m plus 1/2 2 pi. And then we could look at the standing wave when we're dealing with superposition, and I include a Fourier's diagram for it. So these are all the mechanical waves that we're dealing with this chapter. And then there's another topic, extended topic, which is called the waves optics. For the wave optics, we could classify it into single slit, double slit, and diffraction grating. And I included one problem for each of the phenomena. So I'm not gonna waste too much time here. And that basically concludes the whole unit of waves. Thank you.